Hello everyone, welcome to my channel, and we have something new here. See, RTL buffer and RTL inverter gates. This is the circuit diagram. Integrated circuit, transistor buffer inverter gates. We have this layout for the buffer and the layout for the inverter. And we have another circuit here. Here are RTL inverter and RTL inverter. And the other one we have here. Oh, what is this? It's Pikachu. Circuit here, we have here an RTL buffer and a TTL inverter. This is my previous project using RTL technology and TTL technology. This is the circuit diagram of our RTL inverter, and then where is that? This is the DTL, my previous project. You see the diode here, and then the layout. And because we are now going to use new technology for the meantime, it is new. We have now here a new module. This is a TTL technology transistor logic gates. I'm using TTL inverter gates. 2 TTL inverter gates, and I'm going to make a latch switch using this technology TTL. So let us now see the circuit, how it works. And the circuit goes like this. When you push the button here, the output is on, but it never turns up. So I'm going to push another button here, and the output is off. That is now the latching effect of two inverters connected in series with a latch circuit or feedback loop. We're now going to see the circuit diagram of our new circuit. This is the circuit diagram or the logic diagram. We have two inverters connected in series or cascaded like this using TTL logic technology, and we're going to make a feedback loop here from the output of the second inverter going to the input of the first inverter. And let us now see the design of the circuit. This is a TTL Inverter Gate, and this is the circuit configuration. I'm using 5-volt supply. As you have seen here, we are now going to use the emitter side of the transistor as the input side. Instead of the base side, we're going to use the emitter side of the transistor. I'm using 2N3904, and this is now a TTL technology. We have the switch here, switch A, and then we have the input LED. Every time we push the switch here, LED turns on. That is the purpose of LED here. And we have current limiting resistor for the LED. At the same time, provides a ground to the emitter. The emitter is the input side of our circuit. We have the base resistor for biasing the transistor, and then we have another transistor 2N3904 connected the base to the collector of the first transistor. We have here the collector resistor for as a load resistor, and then we're taking the output at the collector to emitter to the ground. This is now our output side using LED, and we have here the power LED, RD3 current limiting resistor to the LED. And let us now use this pencil as a magic wand for our what is this? Oh, it's an eyebrow. Oh, not this one. Here, we're using this. It's Mongol 4A2, my favorite pencil since I was in grade school. So, let us now see the circuit again. We have the power LED, output LED, input LED. As you have seen here, transistor is connected in this way. This is now a transistor logic inverter gate configuration. This is a new technology way back in 1960s of Vietnam War. But today we're going to use the technology. Okay, let us now see the behavior of the circuit. The current flows. Where is the light? I cannot see it. As you have seen here, I have a new figure, a figure 2. This is a diode equivalent circuit of this first figure. Why did I use this equivalent circuit? Because we're going to use this transistor which acting like as a diode or a diode function of the transistor. So let us redraw the circuit. As you have seen here, transistor can be drawn like this. This is NPN type, so we have NPN. And the current flows goes like this. As you have seen here, I set the current of the RB1 this into 1 milliampere. Why did I set the current, or I picked the values of current here? Why did I choose 1 milliampere? Because this type of transistor is capable of switching up to 100 milliamps. So if your base current is 1 milliamps, according to the current gain formula of the transistor, if the collector current, the base current is 1 milliamps, and your current gain is 100, 1 milliamps times 100 equals 100 milliamps to the collector current. That is the current gain formula of the transistor. At the initial state, this is the initial state of the circuit. Once you power on this 5-volt supply, current flows into the BCC, to the base resistor, to the base emitter of the transistor, and to the RD1. Why it didn't flow here? Because it has a lesser resistance here than going to this way. So initially we have this, a symbol for inverter gate, and we have also a truth table. Initially we have a input 0. Since our switch is 0, we got a 0 input here. So when the switch is on the grounded, means there is a potential of 0 volts here. Voltage potential, or voltage at this point, 0 volts. It means it has low. It means it is low. So the current will flow into this node, which is the 0 volts to the ground. So we have a first KVL, BCC minus voltage RB1, voltage at the diode 1, N1, and the diode resistor RD1 equals 0. That is the first KVL, first current law. We got here by transposition, since we know the voltage drop at the base to emitter of this transistor is 0.65 for this transistor. We get now this, our first equation. We are trying to solve for the values of RB1, all the values of the resistor in the circuit. But since we're taking a first KVL here, or using this diode circuit, we have two unknown, RB1 and RD1. So we get this, the first equation. When the current flows here to the ground, since it has 0 volts potential, This makes the transistor to cut off. When this is cut off, the current flows into this node to the RC2 since this is cut off and flows to the ground, to our output. So we have another KBL here, BCC, voltage drop RC2, and then voltage drop of D2. This is the voltage rating of the LED to turn on. So we got 3 volts voltage drop at RC2. Using Ohm's law to compute for the values of resistor here, we know that 3 volts and then 0.02 ampere. The current rating of LED to turn on, we got 150 ohms, and I use 220 ohms available resistor. So we have a second KBL, VCC, RC2, D2 to the ground. Also, the current flows this way. VCC to this node, to the RD3, D3 to the ground. This is a power on LED. That is the, where is that? Here, the red one. We're going to compute for the values of resistor here, RD3. Using KBL, VCC, RD3, D3 is equal to 0. Since we're designing a circuit for this LED, the voltage rating is 2 volts. VCC minus voltage from RC2, voltage from D2, 2 volts, 3 volts. Voltage drop, not this one, VCC, voltage drop at RD3, D3 to the ground. We got 3 volts voltage drop at RD3, and using Ohm's law, direct substitution, since the current flows in the resistor is equal to the current flows of the LED. They are in series, they are equal, and the current rating of the LED to turn on is 0.02 ampere. So we have now the current 0.02 ampere and the resistor value 150 ohms computed value. I'm using 220 ohms available. So we get now 2 values of resistor, RD3 and RC2. Still, we're not getting the values of RB1, RD1. But this is our current lows. BCC, RB1, D1, RD1, also current flows here, second loop, third KBL. Now let us now see what happened if we're going to press the button. What is now the state of the circuit? Applying a pulse or push the switch, just like this one. Pushing the switch, it latches. What is that? But before that latching effect, let us see the effect of pushing the switch here. When you push the switch here, current flows here to the switch A, to D1, to RD1, to the ground. So we have a first KVL, BCC, BD1, voltage drop at RD1. Since we know that the voltage rating of the LED to turn on 2 volts, we got now voltage drop at RD1, 3 volts. Using again Ohm's law, the current rating of LED by transposition, substitution, calculation, 150 ohms. and I use 220 ohms available resistor. So we got now the value of 220 here, 220 at RC2, 220 at RD3. Still we're not getting the values of RB1. How to get the values of RB1 here? Let us now see again. When we push the switch here, current flows to the switch, to the LED. Oh, what's wrong? To the RD1, to the ground. Sending, since this is the input side, sending a high level here, or high voltage here, or logic 1, making this transistor in reverse bias. Since this is reverse bias, what happened is the current flows now into the BCC, to the base resistor, to the collector, base collector junction of the transistor. Why is it that the current flows this way or in this manner? BCC, RB1, DN2 or diode to base to emitter and to the ground. This is now a current steering phenomenon, and we are using a reverse mode of operation of this transistor. So we're always using a transistor that function as a diode here. So let us now see the voltage loop using KBL here. Instead the current flows here, because this is we're sending a high voltage here, or I mean logic level 1 or 5 volts here, making this to reverse bias, this NP junction or PN junction. This is positive, becomes negative here. This is the anode, the cathode side. So it is reverse bias, making this the forward bias. Since this is forward bias, we're now going to compute for the KBL across BCC up to the ground. BCC, RB1, diode, DN2, base to emitter, and then to the ground. Transposition, we know that the diode 0.65 voltage rating of the diode, I mean the diode function of this transistor is 0.65 volts, and then the base to emitter, that is 0.65 volts also. For this type of transistor, we get 3.7 volts across the RB1 using Ohm's law. As I've said earlier, I'm setting the current to 1 milliamps because this transistor can handle up to 100 milliamps. I pick the values of current here by using the formula of the Ohm's law. We know that 3.7 volts, and then the arbitrary values of the current. I'm setting the current to 1 milliamps, which is equivalent to 0.001 ampere, and now RB1 is 3.7 kilo ohms, but I use 3.3 kilo ohms available. So we computed all the values of RB1, RC2, RD3. We computed all the values of the resistor RD1, and we now know the values of all the resistor. Because of that, we're now going to connect the two inverter in series or cascaded. Add latch to two inverters TTL, initial state cascaded. So I'm using now the values of what we have computed here. See the values: 220, 3.3, 220. The configuration of the transistor in TTL, using the emitter as the input, and this is the second inverter. Since our objective is to make this logic circuit TTL 2 inverter in series with a latch switch. What happens if we're going to connect the output into the input? So in here, the same, the output of the first inverter is now the input of the second inverter, and then this is now the output, and then this is new. This is the power LED. This is the new one, the latch. I'm using this resistor from the output of the second transistor to the input of the first transistor, which is the emitter side of this transistor 1. And I also connect a switch here to the ground. That is now the new circuit by adding a latch or connecting a feedback. That's the effect. What is the effect of this feedback loop? Let us now see the effect of this feedback loop. This is now the initial state of the circuit. The current flows. There is no output. What we have here is the power LED on. So this is now the circuit. We only have this power LED on, and the current flows like this without this. Since we're using the switch here, voltage supply, rendering or putting the state of the circuit into 0, grounding the input, since we are going to use this truth table. Switch A is in 0 volts or logic 0. It means it is grounded. So this is state, switch A is 0. Since there's 0 volts here or logic 0, low level, making the current to flow into the base, to the base emitter, to the ground. Because the current flows here, the transistor is functioning as a diode. The reverse mode of operation of the diode is this, or the current steering phenomenon. Since this is the current flows into the ground here, making this to reverse bias. This PN junction, PN, we're using NPN 3904. This is reverse bias, making this transistor to cut off. Since this is cut off, and this line is grounded, we have a 0 logic here, cut off, making the current to flow into the RC2, which is now the output of the first inverter. Now we have here the input of the second inverter. Did you see this? The emitter side. So since the current flows from RC2 to the emitter, is sending a high level here or logic 1. Since this is a logic 1 or high level, making this to reverse bias. This is the negative side of the diode function of the transistor. So when this is negative side, positive side, the cathode, this is reverse bias because we're sending a positive voltage or a high voltage or logic 1 level, making this to reverse bias. What happened is the current flows now into the reverse function of this transistor, reverse mode of operation to the PN junction, PN to the base to collector. And now the current flows here, making this transistor to turn on. Since this is turned on, what happened is the current now flows into the RC3 to the collector to emitter side of this transistor and to the ground. This is shorted, so there is no current flows into the output. That's why there is no output light here, and the latch is inactive. What turns on here is the LED power on. See that? Now let us now push the button. This is now press the button, it latches. When I press the button, it latches. So every time I press the button here, the yellow LED, which is this, is turning on because it's sending the current to the ground, directly to the ground. But it didn't turn off. Why? What happened to this circuit? So let us now observe the current flow. Why it didn't turn off? When you push the switcher, current flows into the ground, to this resistor, to the ground. So we are again sending a current here, which is high level current, which is logic 1, making this again to reverse bias, the diode function of transistor. This is reverse. Now the reverse mode of operation of the transistor, from base to collector, current flows to the base to collector, and forward biasing this transistor. Forward biasing. Okay, forward biasing this, making this current to flow into RC2 to the ground, making this a 0 volts or almost a 0 volts logic here, because we're sending the current to the ground. So this is logic level 0 or 0 volts almost. What happened is the current now flows into the base to the emitter of this second inverter, because this is grounded, so the current flows into the ground, not this way, because it has a lesser resistance and less voltage drop. The voltage drop of the collector to emitter at saturation of this transistor is 0.3 volts, but here to turn on this transistor 0.7 or 0.65 volts, so the current flows here since this is shorted to the ground. So the current chooses to flow from base to emitter to the ground. This is grounded, saturated, because of this forward biasing effect of the reverse mode of operation of the transistor in transistor logic technology. Since this is now in forward bias, it makes this side reverse bias. What happened now is it cut off. Transistor now here is cut off. Since this is cut off, there's no collector current flows here, cut off. So the current now flows into this RC3. So we get now RC3 here. This one, RC3, and to the output. That's why our output LED turns on to the ground, and also to the latch switch to the ground. Why is it not turning off? It didn't turning off because of this latch circuit or the feedback. Once you push the button here, this now activates the latch. making the current this to activate, and it continues to flow the current this state, this green line here, because of this latch switch, latch circuit behavior, making this to activate because of this latch line. So what happened now if we're going to use the second switch, pushing it directly to the ground? Let us use the second switch. It now turning up. What happened here is when I push the switch here, the latch is now flowing to the ground, and since we're sending a 0 volts here, that makes the current to flow in this direction to the ground. Hey, what's wrong? So the circuit now is going into its initial state. When you press the switch to the ground, the latches is gone, and the circuit now is going back to the original state. This is state, because when I push the button here, sending all the current of this latch to the ground. So what happened when this is now 0 volts, now the current now choose to flow into the base to the emitter to the ground, and then when you release it, it's all gone, and the circuit now is going back to its original state. This way, this configuration. That is now our logic diagram with feedback. I'm using a resistor here. Why is it I'm using 220 ohms, which should be equal to the resistor here? Is enough to make a latch circuit. Because if we're using a much lesser resistance here, what happens is if you're going to push the button here, we are sending a current to the output, which is turning this transistor on and making this to turn on. There's a confusion here, so we need to use the same resistor. And I use the switch here, another switch here to the ground, and this is now the logic diagram. We have a truth table here. Our switch is A, and this is the first inverter, TTL technology, and the output Y, which is now the input of the second inverter. And then this is the final output, Y complement. I'm not using Y not or Y bar or Y not. I'm using Y complement. That is my terminology. So when the switch is 0 or grounded, 0, this is 0, inverter, it inverts. The output now is 1. Output, input of the another inverter, 1, it inverts again, 0, so becomes 0. When I'm sending this, using this, pressing the button, it becomes 1 here, becomes 0 here, 1. So you have seen here, when I have input of 1, it inverts, becomes 0, and then 1. Since we have a loop here, it becomes 1, 0, 1, 1, 0, 1, 1, 0, 1, and goes on forever. Because we have latch here. To disconnect the latch, we're going to use a push button directly connected to the ground. cascaded TTL inverter. So we have now here a circuit diagram. I'm using this diagram, schematic diagram. We have here the onboard output and the external output. Then the input, I have input provision and the power. This is now the layout. See here, it latches because of the feedback circuit waiting and pressing the other switch, flowing the current directly to the ground. This is now our new latch switch using the principle of transistor logic 2 inverters connected series with a cascaded or feedback configuration. And thank you for watching the video. Bye bye.